A little late today, 5 minutes late. Sorry. Okay, are you able to see this PPT? Hello?
Yes, sir.
Yeah, in the last class we discussed, reversed load, infinite life problem we discussed. Today we discuss, reversed load, finite life problem we are going to discuss now. Then we move to the Goodman theory and Gorber theory and Schwarberg theory. Okay, so see here, before entering into the reverse load finite life problem, just I would like to go for the basics what we discussed in the last class. Then we come to the problem. Yeah, here, right? I mean, see, this finite life in reverse load condition, we are always considering as a high cycle fatigue. We are always considering this high cycle fatigue because low cycle fatigue, we already discussed why the designer is not showing more interest because of by changing the value of factor of safety, we can successfully design our component in the low cycle fatigue because the number of cycles are less. Less than 10, less than 1,000 cycles, up to 1,000 cycles, right? But in high cycle fatigue, only more importance. In the high cycle fatigue, we discussed already finite, infinite life, and finite life. In the finite life, we are considering high cycle fatigue. In the high cycle fatigue, now here, why we are going for finite life? That's what important. See here, suppose we are designing the crankshaft. We are designing the crankshaft and we are using in our applications, right? Initially, we know that crankshaft material properties, SUT, ultimate strength of the crankshaft, we should know. And ultimate strength we should know, and we should know how much stresses are acting in the crankshaft while doing the testing. For example, the crankshaft material, we gone through the fatigue testing, then we might have been studied the endurance limit strength in the crankshaft, right? Crankshaft material in the laboratory testing, right? But when in practical applications, now we have a standard SN curve based on laboratory test. We have a standard SN curve for the crankshaft material, or the same the crankshaft number of cycle. Now we know from the laboratory test the crankshaft number of stress cycles, how much number of stress cycles, and corresponding to the endurance limit and fatigue life. We know this appropriate value, appropriate data we know, right, from the standard SN curve which obtained from the laboratory test. Then we are going to use this standard SN diagram. We are going to use now. I can say two way. The standard material I may gone through the fatigue test, or else the same model I may gone through the fatigue test in the laboratory. I would like to generate the standard data, right? Now, same material I'm going to use to design, and once I designed the component, I'm going to apply in the actual applications. Okay. Now, once I am applying the actual applications, we know what is the number of cycles, number of stress cycles. we may not know that what is the, I mean, what is that stress amplitude. We do not know that. Then, if we know the number of stress cycles, we have a standard data from in our hand. The standard data obtained from the standard material, obtained from the crankshaft material, or same model. Whatever we are using the same model we might have been tested in the laboratory. We have the standard data. Now I would like to, now the material, the component now subjected into practical applications. I know number of cycles. Then at the corresponding number of cycles, what is the stress amplitude? I would like to find out. And then, hence, we are going for this concept, this finite components in finite life. Then this is, we are considering these 2 points. Just, I mean, yeah, 1 minute. Yeah. This is from the laboratory data, material SUT, crankshaft material SUT. This is our infinite life, endurance strength. We are considering infinite life is nothing but we are considering the y-axis standard. In the abscissa, we are considering log based on 10^6 cycles, because this is under high fatigue life. Okay. Now I know number of cycles. For example, we already got the result, experimental data, standard data. This is standard curve from the experimental. We got it. Now I have the component. Now in practical application, I know number of cycles, how many cycles that a component subjected into, particularly how many cycles now the component subjected. How many cycles, the stress cycles the component completed, I know. Then based on that, I can draw the line. First, we have to draw the line AB. That is standard value. Standard value for the based on material ultimate strength. This is number of cycles corresponding to endurance limit. This is always we are considering 10^6 cycles, right? Then next case, in practical case, I know that material that cranks out how many cycles completed, how many stress cycles. I know that. Then I'm taking that data. Then I'm draw the line in vertical axis ordinate to the vertical axis, y-axis ordinate, parallel to the ordinate. Then where it is crossing that line, where it is intersecting the line AB, corresponding that point, I would like to find out this stress amplitude of my material, my component. Okay. So we can do that through graphical representation, or else we can go for some simple mathematical concept and we can find out what is the stress amplitude corresponding these cycles. That's what our intention, because these are two similar triangles. So up to that we discussed in the last class, and now we go for the problem. So this is the one triangle. Okay. Now this is another triangle. This is the another triangle. Based on this similar triangle, we are going to find out the corresponding stress. If we know the stress amplitude, we will be able to find out the number of stress cycles. If you know the number of cycles, the number of stress cycles, we are able to find out the stress amplitude of the component. Because why do we require? We can evaluate our component condition, either how the component is behavior and how the component is good or bad. We can be able to predict with the help of, approximately we are able to predict the component behavior with the help of this SN diagram. So now we go for the problem. This is the problem we already discussed, the infinite life problem in the reverse load concept we discussed in the last class. Now we move to the problem for the finite life, finite life problem. See the problem, a rotating bar, made of steel 45C8. This is the notation. Okay. We are grading like this material 45C8, and the ultimate strength of the material 6,630 Newton per mm squared is subjected to a completely reversed bending stress. The corrected endurance limit bar is 315 Newton per mm squared. This is maybe obtained from the laboratory. Calculate the fatigue strength of the bar for the life cycle 90,000 cycles. 90,000 cycles. Now, we are considering here this point is our material SUT based on our material SUT. Okay, right? 630, right? That's what we are saying here. See here, 0.9 SUT, 0.9 SUT is equal to then 567 Newton megapascal. Then log base 10 into log base 10 0.9 SUT is this value is going to be 2.7536. That is our maximum value in the ordinate in the y-axis. Okay, stress amplitude. But now see here, this is our standard value of endurance limit stress. Endurance limit stress, standard value of corresponding number of stress cycles. 10/6 we are considering. But we are always, as I told you, that we are starting from log base 10 into 10^3 in 1,000 cycles, right? Then 1,000 cycles because we are considering high cycle fatigue. Hence here I am considering 3. Now, okay. Now this is the triangle A. The triangle. This is the triangle A. Now right? Now that bottom side dimensions 6 minus 3. 6 minus 3, right? And triangle in the y-axis. See here, this is, we know this value, these two values. Then what is the value? 6 minus 3, this value. 6 minus 3, this is a 2.7536. 2.7536 minus 2.4983. 2.4983. Then you 2.4983. Just write this equation because you can easily understand. 2.756. Because this is slightly confusing. Only one problem. If you understand later, you can understand easily other problems. 2.7536 minus 2.4983 divided by this value. 6 minus 3. 6 minus 3. In the right hand side, the similar triangle, this triangle I am taking now. This triangle I am taking now. Okay, that is what is that? We know the stress cycle, number of stress cycles. Stress cycles are given 90,000 cycles. The 90,000 cycles I am considering, I am evaluating the log scale. Log scale 4.9542. Then the left hand side, this is, I take this. This is the second triangle, right? Now the left hand side is 4.9542. 4.9542 into denominator. This is equal 4.9542 minus 3. In the numerator here, this denominator is this one. That's a very simple. Okay. Now what is the numerator? 2.7536 minus log base 10 SF dash. Okay. Now we are able to find out what is SF dash. That's all. This equation, simplify this equation, you are going to get this. That's all. Now the SF is finally we are obtaining this value 386.363 Newton per mm squared. When the component subjected to 90,000 cycles, during that time the component involved into this stress amplitude. The component is involved into this stress amplitude. So this is a finite life problem for reversed load. We may go for the next problem. See here. Now A rotating shaft subjected to the non-rotating force 5 kilonewton and simply supported between two bearings. This is two bearings, simply supported two bearings, and two bearings A and E. Is see here the shaft is machined from the plain carbon steel. They machined from the plain carbon steel. The machining process they given plain carbon steel. The plain carbon steel, what is the surface finish factor? Please, can you tell me that? Plain carbon steel surface finish factor. Yeah. Because we discussed in the earlier class, what is the plain carbon steel surface finish factor? Okay, anyway. 30 C8 material 30 C8 and ultimate strength is given 500 Newton per mm squared, and the expected reliability factor is given, reliability, not reliability factor, reliability 90%. The now equivalent notch radius of the file section can be taken 3 mm. Okay, and here this 3 mm is nothing but this one fillet. What is the life of the shaft? We are going to discuss that only. Now, here the load is acting at the mid portion of the shaft. Load is acting at the mid portion of the shaft here, right? The load is acting at the mid portion of the shaft. Load is acting at the mid portion of the shaft. Now we would like to find out life of the component. Life of the component in the sense in how many stress cycles we are going to find out now. This is the 5 kilonewton given, and the SUT given, ultimate strength is given, reliability given, and notch radius given. Okay. And now we are going to the second step. First we have to find out the selection of failure section. Which section we should consider for the design? See this side, which section we have to, because here they didn't give which section we have to go for the design, but we have to identify based on our earlier understanding. See, this is the diameter 45 mm. This is the diameter 45 mm. But this diameter 35 mm. But this diameter 30 mm. Then this diameter 30 mm, but the load is acting on the middle. When the load is acting on the middle, the equal load is going to be distributed in the shaft and in the shaft also. Hence, which shaft is smaller dia, that shaft we have to consider for finding the life of the component. Because suppose if I am taking this side 35 mm diameter, then suppose if I will find it out, and 10,000 cycles, for example, I am saying that if I am considering 35 mm diameter in the right hand side shaft diameter, considering for the design, then I have found that 10,000 cycles, but this 10,000 cycles valid for 35 mm diameter, but 10,000 cycles much good for even this diameter 45 mm cycle, 40 mm diameter of the shaft. Suppose this cycle 10,000 cycle, it cannot be considered corresponding to 30 mm diameter of this shaft, because this diameter is less and it may go for failure before 10,000 cycles, stress cycles. Okay, hence we would like to consider 30 mm diameter for our design life. Okay, but before doing that, we have to understand the both side, the fillet radius are same or different. Here they have given both side the fillet radius also same. Hence, we would like to take this portion for our design the component and for finding the number of stress cycles in this particular component. Okay, now see here the second, here we are considering 30 mm side diameter in the left hand side. Now come to the SN diagram. This is as usual diagram. This is as usual concept to find out the reaction force at E and reaction force at A, and what is this force are acting here. Okay. So now see here, I mean, this is the bending moments, right? I mean, this is a bending moment diagram. This is a bending moment diagram. Bending moment diagram, corresponding point B, corresponding point is D, corresponding point is C. Now, one more thing I would like to tell you that, I mean, suppose I tell you that because before I told you that without understanding this bending moment diagram, we able to generally we can see that we can assume that this is the region of interest. But I mean, why I'm saying that, suppose you can expect some of the competitive exam without seeing, without giving this, you are able to understand which portion is the weakest portion. That portion is going to be considered for the design criteria. To consider, right? Suppose here, if I mean, it's directly if I give this question in the objective, and which portion is we should consider for the design criteria, you have to understand. Then this portion may be option A, this portion option B, this portion option C. Then straight away you can write it even general observation. Suppose if you want to go for analysis, bending moment diagram and shear force diagram, that way also we can claim that this is the region going to be subjected to maximum bending moment. Hence, I would like to consider this, this region. Whatever earlier I told that general observation. Now I am saying that based on our bending moment calculation, bending moment and shear force calculation. Now see here, even bending moment and shear force calculation, this region is subjected to maximum bending moment. Okay, hence this is the region of interest. But this region is 857 maximum bending moment, but the dimension is more. Hence I don't like to go that region. But this region is smallest diameter, hence I would like to go for the design for this region only. Okay, now I come to the bending moment. Now the shaft is subjected to, already told the non-rotating force 5 kilonewton, right? Then this is simply supported beam. Then we have to find out the bending stress. Then bending stress formula 3m is 3m by z. Then substitute, 32 mb by z pi d cube. Sigma b is nothing but m by z. Then z value, z formula, z value, z formula substitute here. Then you are going to find out bending stress. Okay, bending stress. While finding the bending stress, we are considering 30 mm diameter of this shaft, and here we are considering, corresponding to the bending moment 642.9 Newton millimeter. Okay, and now we come to the standard design. SC is equal to, we already discussed this formula. SC is equal to 0.5 SUT, 250 Newton per mm square. Now the machined shaft surface, this is machined surface, SUT is equal to 500 Newton per mm square. Go to the table. This is belongs to plain carbon steel. Actually, I asked you that, I didn't get any response from your side. I thought you might have been refer your chart, and you may say Ka value, surface finish factor. Okay, if you refer the diagram 5.24, already I showed earlier class we discussed. Then Ka is equal to 0.79 surface finish factor, corresponding to machined surface, and the material subjected into, ultimate strength of the material corresponding to 500 Newton per mm square. Now, for 30 mm diameter, we know the size factor 0.85. This is under 7.5 less than D, less than 50 mm diameter. Then under this category, our surface size factor is 0.85 kb. And the reliability factor from the table we can get it 0.897. And we should now here, this is the the shaft, circular shaft with the fillet, circular shaft with the fillet. Then we should know the R by D ratio. Then we are able to get a stress concentration factor, theoretical stress concentration factor KT. We need that, hence this dimension we need R by D. R by D is equal to 0.1, and D by D, capital D by D is this dimension 45 divided by 30. Then this is we know. If we know these two information, go to the chart, stress concentration factor chart, which we discussed in the beginning of the class. mean in the last earlier classes. Then find out the KT value. KT value is 1.72. We know Ka value, Kc value, KT value. Now we would like to find out actual condition KF, stress constant factor, actual condition. Then we have to find out Q value. Notch sensitivity factor. That notch sensitivity factor also we able to find out because the notch radius is given 3 mm, then 500 Newton per mm squared ultimate strength. Based on these two information, go to your earlier chart. You can find out notch sensitivity factor Q. We know KT, we know Q value. Then based on this, we able to find out this our KF value 1 plus Q into KT minus 1. This is KF. Now once you know KF value, we can find it out KD value modifying factor 1 by KF. Then now finally we are going to find out the actual endurance limit of the component. Actual components endurance limit we are going to find out here using these relations which we discussed earlier. Okay, now this is our actual endurance limit. KB, Ka into KB into Kc into Kd into Sc dash. Now go to plotting the SN diagram now. Now this is our SN diagram. This is going to come in the SN diagram, right? It's the right hand side. We finally the endurance limit strength is 96.637 Newton per mm square. Then you convert, and now we know already ultimate strength 0.9 in SUT, then 450 Newton per mm square. This is the maximum limit in the ordinate, means that vertical axis. Then you convert it into log scale 2.6532, this one, and then log 10 SCE. Here this is our endurance limit strength. Endurance limit, we know that at this one 96.37 Newton per mm squared, convert into log scale 1.98379. Okay, this is endurance limit of the actual endurance limit of the material. Now our aim is to find out what is this SF. They have given number of cycles. No, we are going to find out number of cycles, right? What is our life of the shaft only we are going to find it out. Now here they have given, where it is given, our bending stress is given. We know the bending stress. Material, what is the material subjected? Actual stress. This is actual stress. Actual stress subjected in the material, it's nothing but a stress amplitude. Stress amplitude 242.54. Then corresponding that we have to find out how many cycles. The material, how many cycles completed. What is the life of this shaft? Okay, that's what we are considering here. This is our log based on 242.54. This is endurance limit of this shaft. When we are following this, that material going to reach infinite number of cycles. That is under infinite life. 10 per 6 cycles will be completed. But now at working condition, 242.54 Newton per millimeter squared stress is acting. Bending stress is acting in this material. Then corresponding that, what is the life of the material? That is, we are going to find out finite life of the material. Hence, now I am considering that is my actual working condition. Actual working condition, I converted log scale 242.54 Newton per mm square. I converted log scale. That is now actual scale. Now, earlier problem, we didn't know this stress amplitude, earlier problem. But in this problem, we know this stress amplitude. We would like to find out this. What is this? Number of life, total life of the shaft. Now, similar approach. Just see here. 2. See here. 6.6 and 6 minus 3 divided by this. 6 minus 3 divided by 2.6532 minus 1.9839. This triangle, bigger triangle. Now take second triangle, smaller triangles. Both are similar triangle. Now this is we know. Numerator we know. Denominator we don't know. Numerator we know. 2.6532 minus 2.3848 divided by here. Here what is this? Here. And this is, up to this we know. That's what we are considering. N is equal to log n is equal to 3 plus EF. 3 plus EF. We don't know this one. This one we don't know. Up to this we know. What is this? This is nothing but EF. Nothing but EF. So I can consider in the denominator, I mean log in of EF. I mean denominator is going to be 3 plus EF. 3 plus EF. Even you can write another way. Even you can write another way. Even you can write another way. I mean denominator. I mean log base 10 n minus log base 10 of 3. Log base 10 n minus log base 10 power 3. Such a way that also you can define. You can define. Here I am taking log base 10 n directly. Okay, it's nothing but a 3 plus EF. This value you know, this value you know, this dimension you know, the horizontal dimension we know. What is this? This is nothing but we are always high cycle fatigue 10,000 cycles plus how many cycles are there? That is we are considering. That's what we are considering 3 plus EF. 3 plus EF. You may go like that also. Log base 10 n minus log base 10 of 3. Then finally you are going to achieve same answer only. Then you are going to achieve this is our, I mean this log base 10 into n, log base 10 n is finally you are going to get 4.2030. Then convert it into number of cycles, because now in the log scale converted number of cycles, I mean around 16,000 cycles. Okay, this is the life of the shock. Now I come to, hey, do you have any doubt, please?
Hello, sir.
Sir, yeah, the equation is upside down, sir, I guess.
Which one?
The equation you wrote, sir, if you are different, like taking difference in y for numerator in one side and taking difference for y in denominator and of the one side, sir.
Yeah, you are correct. Yeah, sorry, that's correct. Sorry.
Okay, sir.
And thank you for your correction. Thank you. This should come numerator, right? Am I right?
Yes, sir. We consider it just to confirm. Yes, sir.
Yes.
Continue,
correct.
sir.
You are correct.
Proceed. Yeah.
Yeah, mistakenly I did it. Sorry.
Hello, sir.
Denominator should be like this. This one. This should come. I mean, denominator 2.6532 minus 2.38. Now we are going to find out this one. Yeah. Now I come to this, I mean, cumulative damage fatigue.
Hello, sir.
Yeah, tell me.
Sir, will we always consider lowest diameter as our failure section, like regardless of our bending moment?
I mean, you are asking about this one, right?
Yes, sir.
See, they clearly mentioned that, one thing I tell you, they clearly mentioned that the shaft, rotating shaft subjected to non-rotating force, 5 kilonewton. And hence only we are finding the bending stress. This is the bending stress, actual bending stress, right? But this is our, I mean, endurance strength. When this material going to have infinite number of cycle, at the endurance, when the material going to reach endurance limit strength, this is the stress amplitude, SE. SE is always now less than our bending stress, because now the material subjected to 16,000 cycles. I mean, we are here. Our life, our material life is here. When the material going to reach 10 power 6 cycles, I mean, what we considered always standard number of cycles, 10 power 6 cycles, during that time, this is endurance limit. But in between, we would like to see our life. If we know the stress, we would like to find out our life of the component. If you know the stress. Suppose, if you don't know the stress, because already I told you, the same material or the same component, we already tested in the laboratory. We have the standard SN curve. In the standard SN curve, we are playing. We know the material standard SUT value, ultimate strength value. This is a standard value. Now we would like to find out this life of the component, or else, I mean, stress amplitude at different cycles. So now, hence I'm considering this value now. Hence I'm considering this value because at practical condition, in this condition, what is the life of the component? Are you clear now?
Yes, sir. Thank you.
Okay. Now I come to the next concept. This is, suppose the component subject to cumulative damage fatigue. I mean, cumulative damage fatigue. What is cumulative damage fatigue? I mean, we cannot expect always the component subjected into single stress. I mean, maybe due to some vibration problem, due to some non-linear, complex stresses acting in the component, right? The component may be subjected, the mechanical component may be subjected to different stress levels for different parts of the working cycle, right? We cannot always consider that. Hence, I'm considering cumulative fatigue design. In the cumulative fatigue design, for the cumulative fatigue design, there are stress sigma 1, sigma 2, sigma 3 going to be acting in the component. The component now subjected to, suppose we are considering the component, machine components, fluctuating stress are acting in this component. Fluctuating stress or completely reversed stress, whatever you can say. Now, for example, we can consider reversed stress. In the reversed stress cycles, the component for N1 cycles, small N1 cycle, the component may subjected into sigma 1 stress. The component may subjected to N2 cycles, maybe sigma 2 stress. We cannot say always all the components are going to have same stress, sigma 1 or 2, capital N. Total number of cycles, the component going to have a N1 cycle, sigma 1 stresses. Total N is different, but in the total N, total lifetime N, the component may subjected to sigma 1 stresses in N1 number of cycles. The same component may be subjected to sigma 2 stresses in N2 number of cycles. It is also possible. Then such a way that I can go for up to NN cycles, right? Then in this situation, what is this life cycle? What is the life of the component? What is the life of the component? Please see here, clearly I have mentioned here. When the total life of the component we are going to use this, that guy who developed this concept is called Minor's equation. Suppose the component subjected to completely reversed stress, S1. Reversed endurance strength, S1 at N1 cycles, S2 for N2 cycles, and so on, S3 for N3 cycles, like that. But let N1 be the number of stress cycles for fatigue failure. What is the number of fatigue failure at N1 cycle? N1 by N1 divided by N1. This is now, let N1 be the number of stress cycles before fatigue failure. Before fatigue failure means fatigue life. Before fatigue failure, we are considering N1 cycles. N1 cycle. Okay. While the stress amplitude sigma 1 is acting. Sigma 1 is acting. Then the stress amplitude sigma 1 is acting at a number of cycles, N1 cycles. Then what is the fatigue life corresponding to when we are considering S1, S1 sigma 1 value or S1 amplitude, stress amplitude, then corresponding life is N1 divided by N1. This N1 is total, this N1 is the number of cycles before fatigue failure. If only alternating says sigma 1 is acting. Sigma 1 is acting. Suppose one cycle consume 1 by N1. Fatigue life. One cycle, 1 by N1. Suppose now we are considering this S1 is acting N1 cycles. This is for one cycle, single cycle. When we are considering N1 cycle, N1 by N capital N1. Similarly, I am going to consider N2 cycle, S2. I mean, this is the stress amplitude, S2 for N2 cycles. S2 for N2 cycles, then plus N2 divided by N2. Okay, N2 divided by N2 plus N3. Simultaneously, you can write N3 for N3 cycles plus N4 for N4 cycles. Okay, finally, going to be 1. Going to be 1. The total N1, N2 going to be divided by N. N1 plus N2 plus N3 plus N4, like that. I mean, this is now N cycles. Now see here, now N is here. I mean, N is proportional to damage stress of the level. For example, here, the proportionality of damage fatigue life, we are considering N1 by N1, N1, N2 by N2, up to N3 by N3, N4 by N4. Then, suppose I can write like this, N1 is proportional to capital N. N1 is proportional to N, right? Sorry, here small mistake. It will become a problem. During problem, we discuss this. This is now in the 1. N1 is proportional to N. Because suppose if you know the number of cycles N1, N2 at the stress level, corresponding stress level sigma 1, sigma 2, you know, but you may not know stress levels. What is sigma 1, sigma 1, sigma 1, sigma 2? If you know sigma 1, sigma 2, you may not know N1, N2. So whatever we discussed earlier, we know stress level, but we didn't know number of cycles. Then we used this concept infinite and finite concept. We able to find out this stress level or else number of cycles. Similarly, here if I don't know stress levels, then I am putting, N1 is proportional to N. Then N1 is proportional to N. Then N1 is, I am introducing that, coefficient, that is alpha 1, alpha 2, that is nothing but proportions of the total life. Proportions of the total life. N1 is equal to alpha 1. N1 is equal to alpha 1 in times N. N2 is alpha 2 times of N. This is our proportions of the total life. With respect to proportion of the total life, we are going to consider this. Then substitute this equation. This is Minus equation. N1 by capital N1 plus N2 by capital N2. Then here N1 value substitute here. Finally, we are going to get this value. This also going to be alpha 1 plus alpha 2 plus alpha 3 going to be 1. Alright, now just we go to the problem and then you can easily understand. If you are still not understanding after the problem, you ask me questions. I will explain in another way. No problem. Okay. Now, the work cycle of mechanical, because if I'm explaining the another concept, we are wasting of time. If you are not understanding, then I go for that. Okay. It is very simple. You can understand through the problems. I hope that. Now see here, the work cycle of mechanical components subjected to completely reversed bending stress consists of following 3 elements. One is, this is a stress cycle. This is not stress cycle. This is the S1 or sigma 1, a stress amplitude. Now this is, I can consider the endurance limit 1 also. That's what they put in S1. S1 is nothing but, we are always considering SE. But here, 3 stress level is acting in the material. I am considering S1, S2, S3, like that. This is nothing but stress amplitude in the ordinate, in the y-axis, right? Now, the material subjected into 3 stresses. One is sigma S1. How much time? 0.85 per 80% of the time. 80% of time. This is given. This is alpha. Okay, 85%. Now, 400 Newton per mm squared, 12% of total time. 12% of the time. Okay, now come to this. This is our alpha. That's what I put earlier. Earlier case I put here. Proportionate. When alpha 1 is equal to 1, the material, when alpha 1 is equal to 1, you are considering the material subjected to single cells. Please keep in mind. Okay, when alpha 1 is equal to 1. Suppose alpha 1 is less than 1, the material going to have difference. The material, we are indirectly saying the material subjected to different stress levels. You may expect such a kind of objective questions in any competitive questions, any competitive exams. Okay, now this is 85% of time, alpha 1. 85% of time the material subjected to 350 Newton per mm square. Then 12% of time the material subjected to 400 Newton per mm square stress amplitude. And 3% of time, total time, the material subjected to 500 Newton per mm square. Okay. Now the material SUT is 660 Newton per mm square. This is a standard. We cannot go beyond that because this is the plastic region. Okay. Now ultimate strength. Now the corrected endurance limit of the component. This is a given. This is a minimum given for the component. In this SN diagram, this is given minimum. This is SN diagram. This is our 10 per 6 cycles. This is number of cycles. Yes, sorry, N. Number of cycles, N. This is our number of cycles, N. This is our SF axis. This is number of cycles. This is our endurance limit. S is given. Okay. Now we would like to find out the life of the component in this case. Now our stress levels are here. 3 stress levels are here. S1, S2, S3. But all are above the endurance limit, but below the SUT, ultimate strength. 0.9 times of SUT. 0.9 times of SUT. Now we would like to find out our life of the component while the component is subjected to different level of stresses at a different time or total time of the component. Total time of the end component. Now I come to here, very simple. Now once if you are understanding, the problem is very simple. Now I would like to convert in the log scale. This 0.9 into 660, our SUT ultimate strength. Now convert into log scale 2.7738 in the ordinate y-axis. Okay, and SE. This is our standard endurance limit. Here they are given 280 Newton per mm square. When you are following this, the material going to have infinite number of cycles. Is nothing but 10 per 6 cycles. Now S1 is given. Sigma 1 is given. Sigma 1 or S1 both are same. 2.5441 in the ordinate y-axis. And when you are considering 400 stress level in that during that time, 2.6021. This is during that time. 2.9690 corresponding to 500 stress level. Sigma 1, Sigma 2, Sigma 3, we have calculated in terms of log scale. Now come to the, first I remove this. Now I come to the SN diagram. Now in the SN diagram, we know this is maximum based on SUT. This is based on minimum SC, our endurance strength. This is our corresponding stress cycles, endurance stress cycles. This is always we are considering high cycle fatigue. Okay. Now we are finding the life of the component, but life of the component subjected to more than one stress levels, 3 stress levels. Now this is the equation based on this. EF by ED, EF by EF by EF. Sorry, here this is our equation EF by AE, EF by AE. This is this small triangle. Just I write it. We earlier discussed EF divided by AE is equal to dB by this horizontal axis dB here, dB. Come to this dB by AD. This is AD. Now find out what is this stress cycle here. Log n is equal to 3 plus EF. Always we are considering AD is nothing but our EF is nothing but our EF. Our EF is nothing but E plus log A. 3 plus EF. 3 plus EF. 3 plus EF. Okay. Now, I mean, from this relation, we can find it out. From this relation, we know this is we do not know the y-axis. Log based on E, we do not know because that is because now this is subjected to different stress levels. We are going to find the equation. In that equation, we are going to substitute our different level of stresses to find the component life. Okay. Now see here, from this equation, we can derive that log base 10. We can derive that equation log base 10 n is equal to this way. In terms of log base 10 sigma. Log base 10 sigma. I already have told you, explained to the concept. Then you simplify this, you are going to get log base 10 sigma. But earlier case, sigma is 1. Earlier case, whatever discussed problem. Now the sigma is a 3 level of stresses. Then instead of log n, I am considering at corresponding n1 cycles, my sigma is going to be this one, corresponding to 350 Newton per mm square. What is the stress level? 350 Newton per mm, 2.5411. I am taking this as a sigma 1, this one. Now, corresponding number of cycles I am able to find out. Number of stress cycles. Then based log, this is sigma 2. Next I am introducing sigma 2. This is corresponding to 400 Newton per mm square. 2.6021. Number of cycles. In this stress cycles, during this time, number of cycles is going to be 37,770. Now, the last stress level is 500 Newton per mm square, corresponding log scale 2.699. Then substitute here again here. Then this is number of stress cycles 4,836, 4,865, 65 number of cycles. But one condition we know, this guy is dominating 85% of the life of the component. This guy is dominating 12% life of the time. This guy is dominating 3% of the life of the component. Hence, we are taking Mino's equation to find out the total number of cycle of the component. Alpha 1 is 0.85 divided by number of cycles we know. 0.12 divided by number of cycles we know, 0.3%, 3% corresponding number of cycles we know. Then finally, the total life of the component is 62,723 cycles. Okay, now this is the when the component subjected to cumulative damage in fatigue. Cumulative damage in fatigue means that complexes, different level of stresses are subjected into the material at particular time. In each stress level subjected in particular duration of time. That is nothing but alpha 1 time, alpha 2 of total time, alpha 3 times of total time, alpha 3 of total 3 times. Okay. Now, do you have any doubt? Yeah, someone is trying to ask. Yeah. Do you have any doubt?
No, sir.
Okay. Now, just we see the concept of, the Soderberg line and.
Hello, sir. Sir.
Yes.
Sir, it's already 9:02.
Okay, I stop here. The next class we try to complete. But next week we are going to have, minor one. For maybe you may expect. Wednesday, Friday or Thursday, which one is comfortable? Because you may have some other exam or lab, right? Friday or Thursday?
So next week, sir.
Yes, next week.
You can keep on Wednesday or Tuesday.
Tuesday or Wednesday, huh? Okay, then Wednesday we plan it. Okay. And Wednesday we plan it. And guys, I already have given assignment. Usually I'm giving assignment near the midsem. The students are going to be benefited. So that's what I'm giving near the midsem exam. But in the after midsem, I'm going to every chapter immediately I'm going to give the assignment. Okay. So now this chapter assignment questions also I will give you on Monday or Tuesday. Then those two assignments. I mean, this two assignments you have to submit before next Saturday, not this Saturday, next Saturday. You have to submit those assignments, because whatever assignment I have given early, very simple problems. Some problems are within 5 minutes we are able to solve some problems. Very simple problems I have given. Then some 3-4 problems are complicated problems. I tell you one thing, you have to understand the concept. That's all. Then you can apply the concept for different problems. I take the attendance, then you can leave, please. Sure, we try to complete this topic in the next class. Anyway, whatever we are going to, I'm going to cover next Saturday. That will be our midsem portion. Yeah, do you have any doubts? I come to chat box. Yeah, do you have any doubts? Okay. Yeah, tell me if someone is trying to ask. Yeah, please. DME, yeah. Thank you, Kalyan. I received your attendance. I thought the list. Because I didn't reply. Sorry for that. I will consider that. Okay. In the 20 attendance you gave, no?
Yes, sir.
Now, yeah, please tell me the attendance. Roll number 1.
Present, sir.
Please.